This is part 4, section 12.1. Another definition. Frequency distributions help organize data, but they can still be very unwieldy for large data sets. In these cases, statisticians will often arrange the data into groups or classes. So for example, if you were teaching a large university class of 300 students, you want to get an idea of how they're all doing, but you may not want to tally the number of students who made a 71 in particular. That's a lot of data. It may be more useful for you to tally up the number of people who made a C, which would be all the grades from 70 to 79. That would be an example of a class, the class from grade 70 to 79. And then you'd also do a class for a B, which is 80 to 89, so on and so forth. A frequency distribution based on classes is called a grouped frequency distribution. It's very similar. We'll work with it more or less the same way, but we do have a couple more little definitions. If we consider the group of grades 70 to 79, 70 is called the lower class limit. It's the lower limit on the edge of that class. How do we define the lower edge of that class? And then 79 would be the upper class limit. And notice here, so one class would have started with 70, the next would have been 80, A's start with 90s. They are all 10 apart. The difference between the lower class limits is called the class width. Okay? I have an example problem here, and I want to apologize for the layout. This is one of those things that every time I tweaked one little thing, it messed everything else up in the entire document. I'm still fighting with it. I'm hoping it'll get better. A college professor has students keep a diary of their social interactions for a week, excluding family and work situations. The number of social interactions of 10 minutes or longer over the week is shown in the following grouped frequency distribution. So you have a chart like here. So the number of people who had 0 to 4 interactions was 12. The number of people who had somewhere between 5 and 9 was 16, and so on. Okay? Now what they're wanting us to do, first part, is just get the data off of these. They want us to identify the lower class limit for each class. So this would be the left-hand side here. So 0, 5, 10, 15, 20, 25, 30, 35, 40, 40, and 45. Now the upper class limit for each one, that's this side. So 4, 9, 14, 19, 24, 29, 34, 39, 44, and 49. What is the class width? You want to subtract the first digits. 5 minus 0, so our class width is 5. You do not want to do 4 minus 0. That's not right, because there are 5 entries in here because 0 is included. 0, 1, 2, 3, 4. 5 things in there, not 4. So don't make that mistake. Make sure you're subtracting your lower class limits to find that class width. Okay, so how many students were involved in the study overall? What we want to do is, this is just a shorthand. 12 people said this, 16 people said this. All we have to do is to add up all of these numbers. So add up those numbers, and I don't think you need to see me enter all these numbers into a calculator. I think you know how to add using a calculator by now. If you add them up, and you get 94. So there are 94 students in this study. How many students had at most 14 social interactions for the week? So at most 14, that would be these 3 classes. Because as soon as you hit 15, that's more. So what I want to do to get this answer is 12 plus 16 plus 16. And that is 44. Among the classes with the smallest frequency, which class has the least number of social interactions? Now, this wording could be a little bit weird. They want to know, okay, of the classes with the smallest frequency, what is our smallest frequency? It's 3. So it's these 3 here that have the smallest frequencies. Now, which of these 3 has the least number of social interactions? Well, that would be this one. 35 to 39 is smaller than these. So your answer here is 35 to 39. Another way of organizing the data is called a stem and leaf plot. The stem consists of each tens digit, and the leaf is the ones digit. And basically what we do is we strip apart the stem and the leaf, and we are able to condense the data. We're going to reduce the number of times we have to write down the tens digit. Okay? So if we're given this set of data here, we have 40 elements. And what we want to do, first of all, is I'm going to, right here in my for my stems, I'm going to write down my tens place. So what I want to do is go through here and find the smallest tens and the largest tens. So I have a 60 something and a 20 something. And I still have 60s and 20s. Okay, and that's it. So my smallest stem would be 2, and then 3, 4, 5, and 6. And that is the only time I need to write down my tens unit from now on. Okay? So what we're going to do is that, okay, I want to write down 63. So I go to 60 and write down my ones unit. 48, 42, 42. You see what I'm doing? The tens is already taken care of. I'm just writing down the ones. 38, 59, 41. Okay. I'll come back, keep going. One of the places I make mistakes a lot is I almost did it right here, is I almost plotted 64 instead of 46. It's just easy to make those kinds of mistakes. Okay, so that's a stem and leaf plot. Now, notice how over here I didn't worry about putting these in any kind of order. It really does not matter, but of course the computer is going to make you list them in order. I tried to do it numerous times without writing it down this way first, and I was never able to do it without making a mistake. Just bite the bullet, write it down, and then organize them. Okay? So we're also asked we're asked to construct the stem and leaf plot. But then what does the shape of the display reveal about it? Well, look right here. I mean, this is just sort of a shorthand way of giving us an idea of how many different items we had that started with a 4. How many different professors do we have who are in their 40s or their 30s or 20s? You can just glance at this and tell maybe not the exact number, but more or less. And just glancing at this, it's pretty easy to see that the largest number of professors are in their 40s. Okay, so that's one advantage to this, is be able to sort of glance at it and quickly see what's going on. But the other thing is, and I say this is because mathematicians are lazy, and we generally are, just think about reading these out. 63, all right, 48, 42, 40. How many times are you going to say 40? How many times are you going to say 30? Those are 2 syllables of your life that you're never going to get back again. Here, we wrote it down one time, and we didn't have to write that down again. So the linguistic equivalent of getting to cut off those 2 syllables here, that's what we're doing here. It makes it a lot easier. You have a lot fewer numbers that you could mess up on recopying and things like that. So it's generally useful.